I'll share screen. Yep, ready.
All right. So thanks everybody for coming to what is the last colloquium talk of the semester here at Augusta University in Georgia in the United States. And I think this is about the 15th talk, I think. And so we've had a really great semester, and we get today to end the semester on a great note with a really great speaker, Dr. Derek Dreyer, who's a professor at computer science at the Max Planck Institute for Software Systems and Starland Informatics. And he's done a lot of really great stuff in machine-checked formal foundations and foundations of programming languages and computational logic and these types of systems like type systems and separation logic, which kind of all of these things are going to most likely pop up in the talk today. He's also the 2017 SIGPlan Robin Miller Young Researcher Awardee, so that's a really great honor. And I'm really excited about his presentation today. He's going to be talking about the RustBelt logical foundations for the future of safe systems programming. So thank you very much.
Thank you, Harley. It's a pleasure to be here. This is actually the first talk I've given since before the pandemic started. A first research talk, at least, I've given since before the pandemic started, and so it's good to flex my speaking skills a little bit again. This is also a talk I've given a number of times, and it's always a pleasure because it's kind of representing the culmination of a long line of work that we've been pursuing for the past roughly 12 years on building semantic and logical foundations for what I usually call realistic programming languages. And in the past, by realistic programming language, I usually meant, lambda calculi, which had a sufficiently rich set of features that represented, sort of a wide variety of interesting or technically challenging features that you find in many modern programming languages. But at some point, I sort of always felt like I really wanted to be able to claim with some credibility that these foundations really apply to real and actively developed programming languages. And so that opportunity came up with this RustBelt project. So RustBelt is a project we've had going on for the last 5 years or so at MPI, and we have collaborators at a number of other institutions where we're basically building the first formal foundations for a very young and exciting and actively developed programming language called Rust. So I imagine that some of you in the audience may be familiar with Rust, some may not be. So I'm going to start from the basics of explaining first of all what is Rust and what is it all about and what is the challenge in building foundations for it. So what is Rust all about? Well, I think basically the key thing about Rust is it's trying to tackle this long-standing problem in language design, namely how do you balance safety and control? So on the one hand, we have many high-level languages, high-level safe languages like Java, Go, OCaml, many functional languages that are great for building high-level applications. They provide beautiful safe abstractions, and they make it easier to program effectively and safely. But they don't give you low-level control over resource management, which sometimes you need. And so on the other hand, we have languages like C or C++, or even, of course, sometimes assembly programming, which is critical for building certain classes of applications called systems programming applications. These are think about things like OSs, device drivers, game engines, web browsers, and so for these kind of tasks, you need more fine-grained control over the resources of the machine, and so people typically look to these lower-level languages for that purpose. But of course, that comes at the trade-off of losing safety, and so. So the question has always been, can you somehow get the best of both worlds, right? Can you somehow get a safe systems programming language? And this is the niche that Rust is trying to fill. So Rust has been in development at Mozilla for about the past 10 years. And when I say in development, it was certainly originally developed at Mozilla and continues to have a strong group that is developing the language there. But there's actually thousands of contributors from around the world who are also who've made critical contributions to the language. Mozilla itself has used Rust to build Servo, which is a next generation web browser engine with better parallel performance, which was, pieces of which have been already integrated into Firefox. But it's not the only company that's using Rust at all. There's actually over 100 companies. There's probably that number, the over 100 number came, I think, from when I gave this talk maybe 2 years ago. So it's probably much more since then that are using Rust in production code. Dropbox was one of them. They rewrote their block storage engine from Go into Rust in order to have better control over the memory footprint while still working in a safe language. But and many other companies are also investing in this. Microsoft has made public recently that they're actively investing in Rust. Amazon and Facebook have investment in Rust. There's many companies that have done this. So, but it's not just the industrial investment, of course. The thing that Rust provides, which really no other language has provided, is this combination of low-level control in the style of modern C++, together with strong safety guarantees. In some cases, even stronger than the guarantees you get from other high-level safe languages. So putting all these things together, Rust has the potential, I think, to become, and it's already on its way to becoming the next big thing in systems programming. So enough of this high-level stuff. So let's get a little bit more into the details about what is making Rust work. So the sort of core concept in Rust is that the root of all evil, so to speak, in systems programming is the unrestricted combination of mutation and aliasing. And what I mean by that is when you have an object, say in memory, which has multiple aliases or references to this object, and one of those references is used to mutate the object, potentially deallocate and reallocate the object, and then you're left with anomalies like dangling pointers, use after free errors, data races, if this happens concurrently, iterator invalidation, which is when you have a data structure that's being manipulated while or modified while an iterator is processing over it. And so these are very common problems in systems programming languages. And the key idea in Rust is to prevent all these types of errors statically using a sophisticated type system called an ownership type system. And so the basic idea of an ownership type system is that unlike a normal type system where the types describe the contents or they describe the structure of a value, right? In an ownership type system, they also come with a notion of ownership of the resource or the memory that's backing that value. So for example, if you have a variable x of type t in your scope, not only do you know that x represents a value of type t, but you know that the memory that's backing up that value is owned by your piece of code, and there can't be any other part of the program that can be trying to mutate it at the same time. Now, having just this very simple full ownership discipline is too restrictive in practice. So Rust also provides mechanisms for so-called borrowing. Okay, and this is basically, you can think of roughly borrowing as like passing by reference. So when you pass a borrowed value to another to a function, it's like passing it by reference. But you can create these borrows, and there's two different kinds of borrows. There's what are called shared or immutable borrows, and that's represented by %t, and unique or immutable borrows, represented by %mut t. And essentially, there's a trade-off here between whether you allow mutation or not. If you allow mutation, there can only be a unique mutable reference to the object. Again, fitting in that story of, well, if you allow mutation, then you can't allow aliasing. Or you can make arbitrarily many references to the object, but then you can't use any of them to directly mutate. Okay. So now let me, at this point, I go to demo. Okay, let's see. All right. Figure out how to do this on Zoom. Okay, I'm gonna stop the share and reshare with my desktop. There, okay, good. Right, so here is a simple function, okay? This is just to give you an example, a slightly more interactive example of working with Rust. So this is a very, very simple function. You have it creates a vector v on the first line containing 3 elements, 1, 2, and 3. And then we push 42 onto the end of the vector, okay? And then we go processing over the vector, using an iterator that yeah, it just goes through the vector and prints each item in the vector. Okay, so I'm going to run this, and I think you'll all expect that the result should be 1, 2, 3, 42. Hopefully is this font big enough?
Yeah, it looks good for me.
Okay, all right, good.
Yeah.
Okay, great. So this should be that. There's nothing surprising there. So now what happens if I, for example, happen to put that that call to the push inside the iteration? Okay, so now we're trying to push 42 onto the vector every time we go around the loop. So this is when traditionally, at least in the talk, I would ask. I don't know how well this is going to work in this Zoom setting, but I would ask people in the audience, what do you think is going to happen, or what do you think either what should happen or what does happen?
Yeah, let's do it. So people can unmute if they want, if they're on Zoom, and then if you're on YouTube, just answer the question on the chat.
Yeah, so I think this should be something that's a compile error because you have this immutable reference inside the loop and you're trying to modify it. Right.
So while you're so that's a very that's correct. Okay. Can you explain why? So indeed, when the key thing that's happening in Rust here is when we create the iteration, we borrow v immutably. That's what you see here. And because the iterator only needs an immutable, a shared permission to the vector, but then we're trying while that shared borrow is out to try to mutably access the vector by pushing on it. And indeed, that's what's going to happen. But actually, before you go away, I'm sorry. Oh, there you are. Do you have any? Can you explain why this is good? I mean, why do we want it to catch an error here?
Well, because normally this would be a case where you have some kind of iterator invalidation problem. If you're iterating over a vector using a const iterator, then you would prevent it. But if you have a non-const iterator, then you have the possibility that if you modify the vector and then you try to increment the iterator, you'll miss the value that you just inserted, or you'll walk off into unallocated memory because you changed the size of the vector while you're iterating over it.
Yes, exactly. Right. So that's the key. So I mean, so there's one is the problem of, yes, you might modify the vector in place while it's being iterated over. But the even more serious problem is that, in fact, when you do a push on a vector, that if you run out of the space in the space that's allocated for the vector, it's actually going to deallocate and reallocate the vector. And so you could end up with a crash here because, or with attempting to access deallocated memory if you didn't catch this statically. So this is indeed a kind of common problem. And here, what Rust tells us is exactly what your explanation was, right? We had an immutable borrow that occurred here at &v, and when we did the push, it says a mutable borrow occurs here. That may not be obvious to you that this is a mutable borrow, but that's because there's an implicit sort of cast, if you will. When you call the push function, it expects a mutable borrow of a vector. And so implicitly here, when you write v.push, that desugars into pushing a mutable borrow of v. Okay, good. So
I do have a question about the syntax, though.
Yeah, sure.
How do you know what v refers to? Is the v inside the loop shadowing the v outside the loop? Is there a scoping rule?
No, this is not binding the v. The I is bound here, but the v is referring to the original v.
Okay, and so whether v is mutable or not has changed by the fact
that changed just by virtue of having done this &v in this scope. Now in the scope of the body of the loop, indeed, v is no longer. You only have access to a shared borrow of v.
Okay.
So there's a lot of this often happens in Rust. Actually, there's a lot of sugar to make common programming patterns work without having to having to be too explicit about it.
Okay, so the immutable borrow of v didn't actually get assigned to a variable, but you did it, and by doing it, you have changed what v refers to in the scope of the loop.
Yes.
Okay.
Okay.
Sorry, can I also ask a question?
Sure.
So maybe you explained this before me joining. so excuse me if this is already explained. Now in line 6, when you put that when you don't put that ampersand just before V, would that be a copy of V or would it be an alias for it?
That's a very good question. I'm not sure I know the answer exactly what happens if you put V here instead. I mean, when you are doing, maybe we could test it.
I think it would be into it.
It gives you, it gives you an error because, well, it basically says you have to, it tries to move it into the, this is a somewhat strange error, I think, if you're not used to the type system. I think I don't want to actually get into details of explaining this error.
Sorry, okay.
But it's a good question, actually. And this is funny. I've given this talk a number of times. No one's ever asked that question. It's a very good question. I think the thing is, when you do an iterator, the standard pattern would be you borrow it immutably.
It looks like to answer his question though, if you get rid of the ampersand, it does try to copy it into the loop. And then it gives you some errors saying you can't copy it into the loop and you also can't move it into the loop. And so you're stuck.
Yes.
Well, I mean, it gives you different access to the elements. So if you have the ampersand, you get references to the elements. If you don't have the ampersand, you're going to move the vector, but then you actually have like access to the elements.
I'm going to move on, if that's okay. These are actually very good questions, but I sort of wanted to just give you a flavor of what Rust will do for you statically. So one thing is it may give you somewhat obscure errors if you're not used to the type system, but in the case of this version, of course, it actually gives you a very helpful error. And so this one tells you exactly what the problem is. There's a mutable borrow here. So just to finish the example, I wanted to sort of put what happens if we put the push at the end after the loop. Right, so this is something where you would hope that it does the right thing and says yes, because after the loop, we no longer need this immutable borrow of V because the iterator is finished. But in a simpler type system, that might not be the case because it might think that as soon as you've created these immutable copies of it, well, you have no control over that. But here, actually, the scope of those immutable borrows, the immutable borrow that was used to create the iterator, is limited, right, to the scope of that loop. And afterwards, you know that actually you get back full ownership of the vector. So this is perfectly valid code. So this is just to give you a sort of like very brief flavor of how this works. So I'm going to move back to Keynote. Nearly left the meeting. Okay, that's good. All right. So that was the core idea of Rust, right? Getting rid of this combination, or sort of limiting this combination of mutation and aliasing. However, there's a snag, which is that sometimes you actually need the combination of mutation and aliasing. Okay, so there's actually many data structures that fundamentally rely, at least in their implementations, on having aliased mutable state, right? In other words, a mutating state where there may be multiple references to an object. These are things like pointer-based data structures, doubly linked lists, synchronization mechanisms like locks and channels, memory management mechanisms like, for example, in Rust, reference-counted objects are provided as a library. And for all these things, you fundamentally need mutable state in order to implement the abstraction. So let me give you a concrete example of this, which is how you might implement mutual exclusion in Rust. So suppose you have an object X of type T and you want to share it between multiple threads. There are actually several ways of doing this, but one of the ways you can do this is to wrap it in a mutex and then wrap it. So basically you wrap it in an arc and a mutex, okay? And I'm going to explain these two pieces. So first of all, the mutex provides synchronized access to the object. So it requires that if you want to get access to the object, you have to first call a lock method, okay, to acquire a lock. The other part is wrapping that in an arc, which is an atomic reference counted sort of shell. And the point of that is to allow dynamic sharing of this mutex. So you can make as many copies of this mutex object as you want, and it keeps track of the number of the copies, the number of clones of that mutex through a reference And by the way, one reason I'm explaining this in terms of arc and mutex, there's actually other ways that are maybe more common, but one reason is that I'm going to be coming back to these two data types later in the talk and talking about how we can make sense of them. But anyway, let's to finish this concrete example. So here's a loop that goes 10 times over, and each time it clones the arc of the mutex, and then spawns a thread, which is, and the thread that gets spawned is going to acquire the lock on the mutex, and then once you've acquired the lock and bound the result to this variable y, then you can mutate y, and this is a proxy for the underlying object in the scope of this LED. Okay, and this is actually quite there's quite a lot going on here because there's something very interesting going on here, which is that you are effectively getting shared mutable state. Okay, this is sort of like this is the thing that you might think. From my description earlier, this is precisely the thing that the Rust type system rules out, and yet with this combination of arc and mutex, we got it back, okay, or we got it back at least with the safe under the restriction that you had to synchronize access to that shared mutable state using a lock, okay. So the point of this is that libraries like arc and mutex actually fundamentally extend the expressive power of the core Rust type system. And this makes it very interesting to talk about the soundness of the language. So the reality of Rust is that there's actually a lot of code written in the safe fragment of the language, but there are then many standard libraries like arc and mutex and many others that provide safe abstractions, but internally, in order to implement those abstractions, they must go beyond what you can write in the safe fragment of the language, because otherwise there would be no way to express those abstractions, because those abstractions fundamentally involve shared mutable state. And indeed, what that means is the implementations of those libraries make use of unsafe features of Rust. In particular, they use you'll see in the implementations these blocks of code marked unsafe. Okay, and inside those blocks of code, you could do things like raw pointer manipulations, unchecked typecasts, unchecked array accesses, things like this. So then, the story that's told is that, or the claim that library developers want to make is that clients, as long as clients of these libraries stick to the safe fragment of Rust, they will never observe any undefined or aberrant behavior. But of course, if you're a verification person like me, whenever you hear claims like this, you get very excited, okay? Because you know that they're likely to be false, or at least they're likely to be very non-obvious. So just as a simple example of this, there was this was a couple of years ago. Actually, this was right before the 1.0 release of the language. I remember Aaron Tehran, who was the manager of the project. I'm not sure if he was manager at that time, but anyway, he had moved to Rust, the Rust team the year before, and he was a former postdoc of mine. He wrote this great blog post on this whole sort of approach that Rust has, where you have this safe core type system where its expressive power is extended with various APIs that use unsafe features internally. And the sort of the culmination of his post was this description of this really cool API called scoped threads, which was basically the cool thing about it was it allowed you to spawn threads that had references into the parent thread stack frame. This is something you can't normally do in safe languages. And that was, this was sort of, that was like the pièce de résistance of the whole blog post. Unfortunately, it turned out, I think it was on the day of the post, the day the post came out, or very soon after, that a soundness bug was found involving that library, and it actually was representative of the challenges here, because it actually involved it wasn't that library alone, the scope threads API alone was faulty. It was a combination of that API together with the RC, or the reference counting API. I'm not going to go into the details of what the issue was there, but the point was this was something where each of those APIs on their own was fine, but when put together, you could have memories, you could have use after free. And so this is the kind of thing where you say, well, on the one hand, Rust is doing really exciting things, but they're also very daring. And how can we help this language along? How can we ensure formally that the language is developed in such a way that soundness bugs like this do not occur. And this was the motivation for RustBelt. So the goal of RustBelt has been to develop the first logical foundations for Rust, to use these foundations so that we can verify the safety of the core Rust type system and standard libraries, and in so doing, give Rust developers the tools that they need to safely evolve the language. So when they develop a new API, if they're doing something very sophisticated, they have some way of saying, is this a safe extension of Rust? All right. So I will now go and tell you a bit more about, the rest of the talk is basically, there's in the next part, which is relatively short, I'm going to give you a high level idea of how we do this at a pretty high level, and then go into the core technical idea, the core technical work that enables the RustBelt development. Okay. And if there's any questions, by the way, Harley, please tell me. By the way, is it so we had more questions earlier than I expected. Is it okay if I go over by like a?
Oh yeah, for sure. Yeah. It's no big deal. Okay. Yeah, just go whenever you're ready to be done.
Okay. All right. I mean, it won't go long over, but
yeah, that's the beauty of it.
I found this actually recently when I was giving some talk that I'd given many times before, and it took like 15 minutes longer on Zoom.
Yeah.
So I haven't completely calibrated to the new world order.
Yeah, but that's the good thing, because people can come and go on the internet and we don't even know. So.
Yeah, I know, but I'm not sure if that's positive or not. But anyway, yeah. All right. So so the core question in some sense here is like, when I say that we're proving Rust to be safe, what am I talking about? So the standard approach that people have taken in the past is what's called syntactic safety. And this is an approach that was pioneered by Wright and Felisen in 1994. And if you've taken a programming languages theory class, if you've studied like Benjamin Pierce's book or Bob Harper's book or many other books, you'll learn this approach. And it's a widely applicable approach, and it's very simple. But basically, it will not work for something like Rust. And the reason why is that with a syntactic safety approach, you basically take the notion of whether a program is well typed, and you generalize that to whether a whole machine state is well typed. And then you show that whether a machine state, or that the well typedness of a machine state is preserved throughout execution. And as long as the machine state is well typed, you'll never encounter any undefined behavior. The problem is that assumes that the machine state is well typed, or that you have some kind of syntactic type system that accounts for your entire language. It doesn't say anything about what happens if there's pieces of your program that are written in this unsafe fragment and therefore really don't adhere to any syntactic type system. And so in order to account for the safety of such a language, which, as I've already said, Rust definitely is, you need to generalize to a notion of semantic safety. And I'll try to explain this at a high level. So the idea is that what it means for a library to be semantically safe is that there's no well-typed application using it that can have undefined behavior. That's the goal, okay? And that's, in some sense, that's more or less what I said the goal of the library writers in Rust is as well. How do we make that more formal? Well, the big picture is the following. You basically you build something called a semantic model, and this translates it's basically an interpretation for the types of the language and thereby the interfaces of APIs into some kind of verification condition or safety contract, which has to be satisfied by the implementation of the library in order for the library to be considered semantically safe. Okay, and then there's a couple things you prove about this. One is we prove a general meta theorem, which says that if the implementation of the library is written completely in the safe fragment of the language, then it satisfies its corresponding safety contract by construction. Okay. The other thing we show is that for any library that uses unsafe features in its implementation, there we have a manual proof burden. We have to show that it satisfies its safety contract. But we know then that when we put all these things together, we'll have a safe program. So here's the big picture again, right? We have we have all the code in the middle that's written in the safe fragment, and then you have all these APIs that use unsafe code. And the idea is that when we're done with our job, what we have is a proof that all the stuff in the middle is safe by construction. And for whatever libraries we want to verify to be safe, we have to manually verify those to be safe according to their safety contract. And then we have a general theorem which says you can put all these together. The notion of that the semantic model is compositional. So you can write any client code that uses the libraries that have been verified to be safe, and you know that the whole program will be safe.
There's one YouTube question real quick.
Yes.
Given that you're using unsafe features to implement the library abstractions, could you in principle do the same thing in C/C++? Is the difference here that Rust semantics allows you to prove that it's safe?
Well, the difference is that you have all this code in the middle, right? So that's the thing, right? With C and C++, you'd have to do the manual verification for the whole program. So yes, you can verify that C code is safe, but then you have to verify that all the C code is safe. Whereas here, you only have to verify the libraries that use unsafe code, right? So it gives you a way of encapsulating the uses of unsafe code and being sure that the unsafety will not, or the potential unsafety will not propagate outside of the library. Okay.
Yeah, that sounds good. And there was one other one in the chat.
Okay.
So Saeed is asking, is there any reason to believe that the combination of safe libraries remains safe?
Yes, this notion. So once you have a semantic model where you've proven this compositionality property, right? Basically the property that you can link all these things together, then as soon as you've proven that any individual library is safe with respect to its safety contract, you know it can be composed with any other library that has been proven safe with respect to its safety contract. So it's a compositional notion of safety. Yes.
Yeah, cool.
Okay. All right. So so that's the big picture, and you know, we actually have done this, have carried this out, built this kind of framework for this semantic safety framework for a significant subset of Rust, which we call Lambda Rust. I'm not going to go into I'm not going to go into details really about that in this talk. In fact, we actually have a paper also in Popl 20 on an extension of this. I'll briefly mention that in a minute. But what instead I want to focus on in the rest of the talk is really sort of the fundamental building block that we use in carrying out this effort, because this is a significant effort, and rather than sort of throw a bunch of typing rules at you or whatever, which would not be that informative, I'm instead going to focus on what is really the core that allows us to do this kind of proof. And the question that the central question there, which maybe is not the question you would ask yourself, but is the question you should ask yourself, is what is the right logic to use? So when you're designing these safety contracts, right, what logic should I use? So you might think, well, what logic? I mean, you might not even understand the question. Like, well, you can just use logic, right? Why do you have to use any special logic? The reason basically that we want to use some particular kind of logic is so that we can make our lives much, much easier. So if you pick a logic which, for example, builds in notions that are central to understanding the safety of a type system like Rust, then it will be much easier to build a semantic model of a language like Rust in that logic. And there is a general class of logic. Normally, I would ask the audience to shout out if anyone knows like what general kind of logic I'm thinking of that might be useful. I don't know if Harley has anything to say there, or anyone else.
Yeah,
otherwise, I can just.
I was thinking substructural logics.
Yeah. So okay, that also starts with an S. What I was going with was separation logic. But yes, so that separation logic is substructural. Separation logic is a kind of substructural logic. That's exactly right. So separation logic is so I don't know how many of you have heard of it. It's an extension of for logic. Don't worry if you haven't. By the way, I will be going into detail about separation logic and from the ground up in just a few minutes. It's an extension of for logic. It was developed around 20 years ago by Peter O'Hearn, John Reynolds, Hong-Suk Yang, and others. It was designed as a way of doing modular reasoning about pointer manipulating programs. Although since then, it's actually a number of people have realized that it has applications to a wide variety of kind of forms of modular reasoning about stateful code. It's been a major influence on many verification and analysis tools. In some sense, the intuitive reason why it's a perfect fit for modeling Rust is that separation logic is really another word for it would be ownership logic. It builds into the notion of assertions some notion of ownership. Okay, so assertions basically talk not only about the state of memory, but about ownership, which, as I've already said, is like this key idea in Rust types. So it's a perfect fit for modeling Rust's ownership types. Now the problem, sorry, I spoiled the joke. So there's two problems. Okay, why can't we just use separation logic off the bat? One problem is that there's not just one separation logic. There's actually many separation logics. In fact, much more than 7. It's a problem. So the first separation logic that's sort of relevant for our purposes is concurrent separation logic. This was developed about 15 years ago by Peter O'Hearn and Steve Brooks, and that was a revolutionary piece of work in that it showed that this core idea of ownership was very directly relevant to simplifying reasoning about concurrent programs, and we'll see examples of that. But there's actually there's been a lot of work since then on various variations of concurrent separation logic, and there's a really nice paper called The Next 700 Separation Logics by Matthew Parkinson. This came out actually not long after the original concurrent separation logic, maybe 5 years later. And it has this key line in there which says, in recent years, separation logic has brought great advances in the world of verification. However, there is a disturbing trend for each new library or concurrency primitive to require a new separation logic. Okay. And he was arguing we shouldn't do that. We should somehow figure out the right core logic. Indeed, this is a serious problem. Right? If we're building our model, our RustBelt semantic model, by interpreting the types of Rust into some separation logic, and then it turns out that for some new library that someone comes up with, they can't prove it's safe according to that logic, then the whole thing goes out the window, right? So we need some kind of universal, in some sense, separation logic, some separation logic to rule them all, right? In which you can encode a variety of forms of sophisticated reasoning to prove that individual libraries are safe. The second problem, which I'm not really going to focus on in this talk, but I want to mention it because it was a big part of the RustBelt project, is the memory model. So basically, all the logics up until the last couple of years assumed sequential consistency for memory accesses. Certainly the first 7 of them did. And so what is sequential consistency? It's a very standard model of concurrent memory accesses where you basically assume you treat each memory access to shared memory as if it has global effect. So every other thread can see the mutation immediately. And this is just not realistic for high performance concurrency, and it's not realistic for Rust. Okay, so for Rust concurrency libraries do make use of what are called weak or relaxed memory operations that have much weaker effect. They don't, when you do a write to some shared memory, it's not visible to all threads immediately. It's not necessarily, all threads don't necessarily see memory accesses to shared memory accesses in the same order. And so you need to have a logic which accounts for this. So this brings me to sort of the whole line of work that we've been doing on building logical foundations for, as I said, sort of realistic programming languages, but ultimately that we've applied them to Rust. And there's been a couple lines of work here. One, which is the one I'm going to talk about most today, is Iris. So Iris is sort of a high-order concurrent separation logic framework that's implemented in the Coq proof assistant, which we originally designed as a way of sort of simplifying and unifying modern separation logics, trying to answer this question from Parkinson's Next 700 Separation Logics paper. But we've now explored this enough that I feel confident saying this is I don't know if it's a universal logic, but it certainly is widely applicable to many different kinds of problems. GPS was some work we did several years ago where we built sort of the first modern, fully featured concurrent separation logic that handled the full, or something approaching the full C++ memory model. There's actually been quite a longer line of work since then, but that was attempting to handle this problem of developing logics for relaxed memory. And then there's RustBelt, where we actually put all these things together. We build this semantic model on top of a logic which combines features of Iris and GPS, so that we can handle Rust libraries as they are. So in the rest of this talk, I'm going to not really talk about GPS or RustBelt. I'm going to focus on Iris because that's really the central technology that is enabling the whole development. And I'm going to try to explain it from first principles. So I'm not assuming you know anything about separation logic, and certainly not about concurrent separation logic. And I'm going to try to show you how this, I'll first review how concurrent separation logic works, and I'll illustrate that on the mutex example that I showed before. And then I'll talk about, what was missing from concurrent separation logic, what Iris brings to the table, and how we use that to reason about the arc data type that we showed before. Are there any questions, Harley, on the YouTube?
Nope.
Okay.
So you're good to go.
Great. So Great. So I'm starting with the basics. So I imagine that most of you have seen OR logic before. I hope I don't know if in your class, if Harley, if that's a reasonable assumption that people have heard of it, but
I've mentioned it, and there's a few professors that mention it in their other courses as well.
Okay. Yeah. I mean, it's so this is a very old, classic technology for program verification. And I'm going to give you the very short version. The very short version is there's some code we're verifying. That's the C in the middle. There's a precondition, which is this precondition P, which is some assertion about the state of the program before C executes. And there's a postcondition Q, which says that, well, actually the whole OR tuple is going to say that C is safe to execute under that precondition. And if it terminates, it will produce a state satisfying the postcondition Q. That's that ends my tutorial on OR logic. So sorry if you want to know more. I mean, yeah, there's plenty to read. But for the purpose of this talk, that's actually all you need to know. So what is separation logic? Well, basically, separation logic extends OR logic with a couple key forms of assertions and techniques for reasoning about them. So this is sort of classic vanilla separation logic. You have one of the key assertions is the so-called points to assertion, X points to V, that's written over here. That says that not only does location X in memory point to the value V, but in fact, we own that location, where we is basically whoever is asserting X points to V in their precondition. So if I'm a thread, for example, and I'm verifying a thread of code, and I assume X points to V in my precondition, that means my thread owns X, and I know no other thread that's operating concurrently is going to access X. And then the other bit which is essential, is this notion of separating conjunction, written P star Q. And P star Q means that P and Q are assertions about that describe ownership of disjoint state. Okay, so it's different parts of memory. So for example, if we can assert that X points to V star Y points to W, then this means not only does X point to V and Y point to W, but also X and Y do not alias. In other words, X is not equal to Y. Okay, those two locations are distinct. So now what do you do with these things? Well, there's basically two forms of reasoning about concurrency. Okay. Sorry, that was my tutorial on separation logic. Now let's move to concurrent separation logic. This is warp speed tutorial. But we'll see an example in a minute. So the first major rule is the parallel composition rule. It's a very simple rule. It says if I want to verify a program that is concurrently running C1 and C2, okay, that's what this parallel bars means, then I can actually verify them completely independently, so long as their preconditions are and their postconditions talk about disjoint state, okay, which is indicated by the fact that you have a separating conjunction in the pre and the post. So intuitively, this makes sense, right? If I have two threads that are working on different pieces of memory, they don't interfere at all. So I don't have to care about the interference. So let's see an example of that. So suppose I have one thread that's star X equals 3, it's updating X to 3, and the other is updating Y to 4. Then the way I verify this is I use the parallel composition rule to split this into two subproofs. One which just says, well, if I have X points to 0 and I set X to 3, then I get X points to 3, and the other one says if I have Y points to 0 and I set Y to 4, I get Y points to 4. And then at the end, you just join them together with a separating conjunction again. Okay, that's it. Very simple. So this is kind of like the poster child for concurrent separation logic. This is where everything looks beautiful, and there's no unnecessary reasoning. However, of course, as we saw before, right, life is not so simple, right? You actually have shared mutable state, which is exactly what's missing from this picture. So if you want to reason about shared mutable state, then you need the other key mechanism of concurrent separation logic, which is invariance. And the idea of invariance is that if you have some piece of shared state that multiple threads are operating on, you establish an invariant on it, which I'll write here as invariant R. Okay, I'm not going to show you exactly how you establish the invariant. That's more detailed than I'll go into. But let's say we've established that invariant. Then the idea is if I'm verifying some piece of code C, then the invariant rule, what it lets me do is it lets me temporarily gain ownership of that shared state represented by the invariant R. I put that into my precondition. Note that it's starred because basically that piece of shared state has got to be disjoint from any local private state that I own, which was described by P. And then at the end of C, I have to reestablish the invariant R, okay, again, disjointly from my postcondition Q. and then I lose it in the actual conclusion of the rule, okay, because it goes back into the shared state. So basically, the idea is if I'm reasoning about the way you reason about shared state is when it's your turn to apply the invariant rule, you get temporary ownership of the shared state. You can do whatever you want with it, and then you have to put it back in such a way that it preserves the invariant again, and then it gets released back into the shared state. That's the mode of working with this rule. Now you'll notice there's this important side condition here that says C is atomic, which means it takes one step of computation. So so ordinarily when I give the talk, I would ask if anyone in the audience has any idea why we need this this side condition, because it's quite important. I don't know if anyone has.
Nothing on YouTube answering that one.
Okay. Yes.
Yes. It's because, is it because you have two different, you might have two different applications of this rule and they both rely on the same invariant, and so
Yes.
you don't want, this thing has to be atomic, you don't want it to see changes made by someone else?
Yes, exactly. You could have two threads that are both trying to access the shared state at the same time. If the applications of this rule were overlapping in time, then you would have interference. Okay, but by doing it atomically, you basically are sure that, well, there's no, when you're reasoning about an atomic step, you know there's no interference from any other thread, at least in a sequentially consistent memory model. Of course, things get more interesting when you have a relaxed memory model. But yeah, I'm talking here about the traditional sequentially consistent memory model. So that's the idea exactly. So this avoids interference. Thanks, Jonathan. Okay.
There's one question on YouTube. Sorry.
Yes.
So the question is there something analogous to weakest preconditions here too?
Yes. Well, basically, formally in Iris, we actually only have weakest preconditions. So actually, the Hoare triple. I've been writing everything with Hoare triples because that's a more familiar notation. But basically, PCQ in Iris gets translated into essentially P implies weakest pre-CQ. So I don't know if that answers the question, but yes, we actually work with weakest pre directly all the time. Cool. But in traditional presentations of separation logic, they're done with Hoare triples. So I'm following that standard presentation.
Yeah, thanks.
Sure. Okay, so let me move on to an actual example here. So, so suppose we want to in CSL verify a simple mutex. Okay, so here you have a mutex that has it's represented in as just a pointer x to either 0 or 1. Okay, so it's just a lock, which is 0 if it's unlocked and 1 if it's locked. And the idea is that this is going to be gardening some state, some resource. But let's look at the implementation first. So first of all, the implementation is very simple. It just says for lock, you spin, okay, trying to do a compare and set on X, trying to set it from unlocked, the 0 state, to the 1 state. And once you succeed, then you are done. So if you're not familiar with it, CAS is this kind of primitive concurrent atomic operation you have in languages like C and also in Rust. So that's the lock, and the unlock just sets it back to unlocked. Okay, it doesn't have to do any kind of CAS because there's no contention for setting it back from locked to unlocked. Okay, so here's the specification that we will be proving in concurrent separation logic. And it's a very simple one. It says, suppose we're gonna let P described, and this P is a parameter of the whole proof, of the whole spec. P describes some invariant on a piece of shared state that's going to be protected by this mutex X. Okay, and then the spec for the mutex just says under trivial precondition, anyone can call lock on X. Okay, which is true, right? You can have multiple threads they call lock with no precondition, and then once you've succeeded, once lock returns, you own P. You own that shared state. Okay, and then in order to unlock, you have to provide P in your precondition. Okay, you have to basically show you've reestablished that invariant on the shared state. And then in the postcondition, you just get the trivial postcondition true. So you've lost P, right? When you call unlock, you give up P in your precondition and you sort of you get back nothing. Okay. So this is the spec. So let's see how we verified. Oh, sorry. Before I show you how verified, this is how you would use this spec, right? So so you might have two threads that are both have critical sections protected by lock and unlock, and they both have trivial precondition true and trivial postcondition true. So you can verify them completely independently. And each one just calls lock, it gets P, does whatever it wants with the resource described by P. By the way, internally in that critical section, it could break P. P doesn't have to hold consistently throughout the critical section. But at the end, P has to hold, and then you unlock. Okay, and those are verified completely independently using the disjoint concurrency rule that we saw before. So here's now the question is, how do we verify it? Well, I mean, the mutex is a piece of shared state, so we're going to verify it by establishing an invariant, a shared state invariant. In this case, the way the invariant will look is the following. It's a disjunction between two possible states corresponding. You can think of it as a two-state machine, the unlocked state and the locked state. Okay. In the locked state, you just have x points to 1, because in the locked state, the invariant, which is describing the shared state, doesn't have anything, right? In the locked state, whichever thread has acquired the lock has taken control of P, and in fact, P may not even hold. In the unlocked state, you know that the lock is set, that x is pointing to unlocked, in other words, 0, and you know that the shared state owns that resource P. So with this in mind, now we can go try to verify. I'm just going to show you how you verify the lock function. Okay. So remember, this was this sort of spin lock. So basically, this boils down to the key step is there's the boring case which is where the CAS fails. Okay, that's not very interesting. You just retry. So I'll show you the case where it succeeds. All right. So in the case, yeah, there's basically two cases in the state transition system. One is when x points to 1. As I said, that's not the interesting case. The interesting case is when the CAS actually succeeds. And here we want to show that the result we get out is P. So how do we do that? Well, in this case, we know that we're in the unlocked state. So using that invariant rule that we said before, right? We transfer ownership of the shared state invariant into our precondition. Right? This was the R that got starred onto the P in the invariant rule. So we take that temporary ownership, we get x points 0 star P. Now we have x points to 0 in our precondition, so we're allowed to safely do the CAS. And when we do the CAS, it has the effect of modifying x points to 0 and taking it to x points to 1. Now that we've done that, we are actually in a position to restore the invariant, except now we're going to have to change the state, moving it to the locked state, because we're going to put the x points to 1 back there. Okay. And notice that what we're left with in return is P, and that's exactly what we needed to show. We needed to show that we got access to the shared state described by P. So that's the whole proof. Okay, it's pretty simple, and this is a pattern we're going to see again in a few minutes, but in a somewhat more involved example. Okay, so to give a recap of CSL, basically you have two rules: a parallel composition rule for disjoint concurrency and an invariant rule for shared state concurrency. And as we've seen in this example, they work hand in hand. Any questions?
So where is this shared place that you're putting stuff when you take it out of the preconditions? I don't really see that in the model.
Well, I didn't show you the model, but so what do you mean exactly by where is it? I mean, so you can sort of. I think I know it. Let me see if I can answer your question. So the way you can think about it is there's a bunch of threads that are being verified. Each of them has precondition, whatever their current precondition is. Okay, that describes their local state, the state they own privately. Then there's the state described by all your resource invariants. These like in this case, it's this thing. Okay, and that is the state. So this is a disjunction. Right? This state is so at all times there is some piece of state disjoint from the local state that satisfies the local thread's preconditions, that satisfies all the invariants that have been established. And so basically, what happened when we did that CAS step in the lock was we transitioned from a piece of state that was satisfying the left disjunct to one that was satisfying the right disjunct in that one step. But both before and after the step, this invariant was satisfied. It was just satisfied with a different case of the disjunct.
Okay. And is that what you represented by taking and putting back stuff from the
in some sense, I mean, I'm animating this to give you a visual sense of it. But yeah, basically, you can think of it as within one atomic step, you're allowed to open up any of the shared invariants you see, that you know about, gain local access to them, do whatever you want with them, and then reestablish them within that. As long as you do that all within the same time, the same step of execution, then it's safe. But you have to, but before and after every step of execution, there has to be some piece of shared state disjoint from the local state of any thread that satisfies all the invariants. Okay.
And so in this case, first, the piece of state that satisfies the invariance is x points to 0 star p.
Exactly.
Then
afterwards, it's x points
it's
to 1.
x points to 1.
Yes. Thank you for the question. Okay, so moving on. So that was CSL. Okay, so this is in some sense review, but I mean, most people in the world have used CSL, so I figure it's important to explain this. So then what do we do? Well, we have to go beyond CSL. Why do we have to go beyond CSL? Basically because this mechanism of invariance that I've described is not enough, okay? It's enough for the mutex example I showed, but it's not enough in general. And so modern CSLs, all the, the million Supermans that I showed before, those basically generalize invariance in a variety of ways. And there's essentially two ways in which they generalize them. One is they generalize them to describe how state changes over time. So for example, you might want to know that, not only, well, you might have some shared counter and you want to know that over time, it only increases in value. Okay, that's the kind of thing that comes up frequently. That's a kind of, in that example, it's kind of monotonic state change. And the other is you want to be able to control who is allowed to make changes to the state. So this is typically represented by concepts like permissions or tokens or capabilities, right? And it might very well be, I mean, it frequently is, in fact, that throughout the course of some algorithm or some operation, which thread is allowed to make a change on some shared state changes. In fact, these permissions, these tokens, these capabilities are themselves resources which can be passed around through the invariance in much the manner that I showed, that resource invariant P passing hands from the shared state to the local state of some thread. So you can get quite involved with these kinds of extensions of CSL. And indeed, when we started this work, there were many, many different CSLs. In fact, there's still more since this is an old picture that was done by Ilya Sergey. So the fact that there's many different logics is not necessarily so bad on its own, but the rules of these logics were quite involved. These are like primitive rules of logic, which are proven sound with respect to some model of logic. And this is difficult because, I mean, having complicated rules is, sometimes in life there's complicated rules. But the problem is more that each logic has its own complicated rules, and they have different models for all the logic. So if you want to take one complicated rule from one logic and try to integrate it into another logic, there's no sort of common ground on which to determine whether that's a sound thing to do. So we thought, okay, there must be a better way. And actually, this whole Iris project came out of a desire to write a book, which we still haven't done. But at the time, we wanted to write some sort of monograph on developing semantic models using separation logic and so forth. And we couldn't figure out the right separation logic to use because there were all these crazy ones. Like the one at the top, by the way, is one that I'm responsible for. So I'm not, I'm complaining about myself as well. We felt like there has to be some simpler thing. So this is where Iris came about. So Iris is basically, the idea of Iris is a very simple one at a high level. We'll get into some details about what it actually looks like. The idea is that all you really need to consolidate these extensions to CSL are two things. One is invariance, a slightly more complicated form of invariance, but I'm not going to get into that, from CSL, plus the thing I am going to focus on, which is user-defined logical state. Okay, sometimes called user-defined ghost state. Using just these two mechanisms, you can actually derive the rules of some of the most advanced extensions to CSL that people have studied. So instead of sort of going into the whole theory of Iris, I'm instead going to try to give you a sort of example-driven presentation of this, especially because I don't have that much time left. In fact, I'm already over. So I'll try to go through this example relatively quickly. So I'm going to show you the ARC example, right? So this is this ARC data type. This is an atomic reference counted data type where you take some data and you want to share it and keep track of how many copies there are. And you do that using a reference count. So here, I'm representing it just as a data structure, a struct with two fields. One is the underlying payload, and the other is the reference count, CNT. Okay, and there's going to be three operations on the data type. One is called x.clone, and this says you first do a fetch and add, which is another of these atomic operations that atomically increments the count field by 1, and then returns x. So in fact, you return exactly the same thing you got before. So the clone is no different from the original object. They're just aliases, but the count field has been updated when you did the clone. The print here just accesses the data, and the drop field decrements the count. So drop is the destructor for ARC. it decrements the count, and then if it notices that it's the last one, then it just frees the underlying object. So to specify, so how are we going to specify this thing? The idea is that we're going to use an abstract, what we call an abstract predicate, arc of X, which you can think of is it's essentially representing the semantic model of the arc type in Rust. And what that means is you can intuitively, arc of X represents the permission to access shared data through this reference X. Okay, so with that intuition in mind, let's talk through the spec. The spec says, the first line of the spec says, for clone, if you know that arc of X, if you have arc of X, right? In other words, X is an arc object. Then when you get back from clone, then you still have arc of X, and you also now disjointly have arc of Y. Okay, where Y is the clone. For X print, you get the same thing back because you still want to be able to use the arc after you've done the print. And after you do a drop, you lose the arc because, of course, when you're declaring the destructor, you no longer have the object anymore. So I don't know if anyone notices anything sort of a little, given this whole description of separation logic that I've talked about so far, is there anything a bit fishy about this spec, particularly the clone spec? Oh, I can't hear you, Arlie.
Oh, I was answering in a way that no one's supposed to know, but.
Is it the problem that there's no rule that starts with true? You always have to have arc of X.
Oh, no. That's just because I didn't show you the constructor.
Okay.
No, that's not the problem.
I think it has to do with the Y just becoming created.
Well, I mean,
and the fact that Y has some of the stuff as X.
Right. Yeah.
Exactly.
Yeah.
So the problem is not with Y being created. The problem is that you have arc of X star arc of Y, which implies that they're disjoint, and yet we know from the implementation of clone that Y is equal to X, right? So we actually have really arc of X star arc of X. So how can that possibly be? They're talking about the same state, and yet we have a disjoint, what seems to be a disjoint conjunction here, right? So the key here is that this is okay because arc of X is purely logical state. It does not describe physical ownership of the heap. Okay. So what does that mean? So basically, what ownership of logical state. So this comes back to this key idea in Iris that you can define custom notions of logical state, which can have a separation algebra on them, and you can develop axioms about those notions of logical state, such that things like arc of X star arc of X make sense. And in particular, in the proof of this arc, we're going to rely on two axioms about a certain model of this logical state for arc, which I'm not showing you in detail. And here I'm just going to show you the axioms, and then we'll see briefly how they're used in the proof. So the first says that I'm sorry, I forgot to mention. In order to state these axioms, we need to not only have arc of X, we need an additional predicate, which I'm going to call count of Xn. This also describes logical state, and it basically asserts that currently there are n outstanding arc of X's in existence. Okay, so the first rule here is a kind of agreement axiom, or what we call an agreement axiom. It says that if I know that there are n outstanding arcs in existence, and independently I exhibit that I have one, right, because I show arc of X, then clearly n has to be greater than 0 because I just showed that I have an arc of X here. And it has to be at least 1 because I have this one. The other axiom is this one here, which says that if I know that there are n outstanding arcs in existence, then I can create one by applying this rule left to right, and I get an arc of X out on the right, and simultaneously I bump up the count by 1. Okay, and I can also go the reverse direction and consume an arc and go back from n plus 1 to n. Okay. So these are the two axioms we're going to add. Again, I'm not describing. What you should ask yourself is why is he allowed to just start putting axioms on the screen? Okay, that's a very good question. I'll come briefly back to that at the end. But this is what we'll do for arc. And now once we've done this, we can now describe the invariant of arc. The invariant says, first of all, that at all times there exists some number n which describes the number of outstanding arcs. Okay, that seems relatively uncontroversial. And additionally, we have that either n is 0 or x points to a struct with two fields where the count field is n. So you can think of this invariant, and so the reason for this disjunction is just that once the count field goes to 0, then the object is the arc is deallocated. Okay. So what this invariant is doing is it's tying the logical state, which is represented by count xn, which tells you how many arcs are logically in existence, together with this physical state that says what the count field of x is. Okay. So in some sense, the logical state gives it meaning. So now having this in hand, well, first of all, actually, before I show this, this is a visual version of the same of that same invariant. It says there's basically a state machine where you can go back and forth between n and n plus 1, and n here represents the logical state count of xn, and so for example in the 4 state, you know that actually the invariant owns x points to 4 and then some data, okay, and etc. for all the types except in the 0 state where there is no ownership of x anymore. Okay.
We got a couple questions.
Sure.
One question from YouTube was back when we were talking about the problem with y depending on x. The question is, what about shared data that can be accessed in a mutable way? Chatting about the fact that.
Yeah, we do. Sorry, was this going back earlier, or was this?
Yeah, yes. To when we were talking about the problem with we had arc of x and then arc of x.
Sorry, arc of y. Oh, okay. Yes.
Yeah.
Right. Oh, you mean just so? How is this not totally break separation logic? Is that the question? Maybe intuitively. I mean, so intuitively, the idea is that for this logical state. The idea of separating conjunction is that if I have a separated conjunction between two things like arc of x and arc of y, then I could give them to 2 different threads, and those threads don't have to worry about any interference. Okay, they're separable. They're separately ownable resources. Okay, and intuitively this makes sense, right? If I have a bunch of arcs, I can give them to as many threads as you want. They can all call clone whenever they want, and there's no problem. There's no unsafe interference. So that's the intuition for why this works. To give a more precise example of formally why this works is that gets more detailed.
Yeah, thanks. Yeah, so it was Michael who asked. So if that didn't satisfy, just let us know. We can ask another question. Another one is in the chat. It says, should the disjunction be inclusive or? This is, I think, the disjunction you showed, I mean, on the previous slide or a couple of slides. Yeah, I think they're talking about
it is, or disjunction in separation logic is inclusive, but it doesn't really matter here.
Does it really not? Because if n is 0, then does it really make sense for x to own anything?
Oh, it doesn't. That's the point, right? So if you were to arrive at a case where n is, well, actually, you know, this is a good question. We're going to get to this in like literally the next slide. Actually, this was exactly my next point. So maybe we'll take this point here, right? So what I would normally ask is, so like, notice that each of these operations takes arc of x as a precondition. Why is that useful? Or what is the thing? There's a bit of reasoning that happens in verifying each of these functions. And what is that reasoning that depends on arc of x? But okay, I'm sort of, since I said this is related to your question, I kind of give it away. So the answer is each of these functions is only safe to do if x is actually allocated. But because we have arc of x, we actually know that x is allocated, right? Because we have that axiom, that agreement axiom, and the invariant tells us that if we have count of xn, which we get from the invariant, and we have our local ownership of arc of x, then we know that n must be greater than 0. And therefore, that rules out the 0 disjunct of the invariant, right? And we have the invariant over here. That rules out the possibility that n is 0 because we use the agreement axiom to show that n cannot be 0 if we can demonstrate an arc of x. So that tells us we have to be in the right disjunct, so x is allocated. And so all these operations, which all involve accessing x, are safe.
Okay. Thank you.
Sure. Okay, so now I'm going to quickly show, I'm running over time. I'm going to quickly show how we verify clone. And it's going to follow the same pattern that we saw with mutex. Okay, basically this kind of idea of, you know, you open the invariant, you gain access to the state, you do some manipulation, and you put back the state. The difference here is that we additionally have this logical state of the count and the arc, and we're gonna apply some axioms to work with those. So so basically, right, what is the y equals x dot clone? This is essentially just doing a fetch and add on x, and then you return arc of x star arc of x. We've seen this already. Okay. So this is an atomic operation, so we can apply the invariant rule. Okay. So we know, as we've said already, we know we're not in the zero state. So we could be in any of these other states. For purpose of visualizing this on the slide, I'm going to suppose that we're in the state where x's count field is 2. Okay. But it could be, of course, the reasoning here is independent of which positive number it is. So what happens in this state? Well, we apply the invariant rule. So we can move ownership of the thing from the invariant, the x points to 2 something, into our precondition. Now we have ownership of x locally, so we can do the fetch and add, which just updates x's count field to 3. And now we want to put this back into the invariant, right? That would be the same pattern that we saw before with mutex, but we can't yet, okay? And the reason is that we have a disconnect between the physical state, x's count field points to 3, and the logical state, the count x. We have count x2 in the in the invariant here. So what do we do? How can we fix this? Well, we have that axiom, right? Remember, we have this axiom which says if we have count n, in this case count x2, that's what this represents here, we can update it to count x3 and thereby spawn off an arc of x as well. So we shift to the 3 state and we get arc of x by applying this axiom. Having done that, okay, so that's really in our current proof state. We now have the logical state is at 3 and the physical state is at 3, and so we are in shape to restore the shared invariant and the application of the invariant rule. And what are we left over with in the post condition? Well, we have arc of x star arc of x, which is exactly what we wanted. Okay, so basically we do this physical state update from 2 to 3, and then we do a logical state update along with it to preserve the invariant that shows that they're connected. Okay. So this is the flavor of how, I mean, I've shown you sort of proof by animation here, but this is actually how proofs look like in Iris. I mean, okay, things aren't flying around, but the structure of the proof and the number of steps, et cetera, is exactly the same as what I just did.
One quick
yeah, sure.
If you don't mind.
No, not at all.
How do you ensure consistency of the set of axioms?
Yeah, that's the next slide. Okay.
People are just writing the top.
I'm glad that people are, paying attention. It's good. So I did try to design the slide so that I would answer the next obvious question. Okay. You're right. So how can you basically? You might say, Derek, you pulled the wool over our eyes because you just took this problem of proving safety of this physical, state manipulation and turned it into a problem of proving the soundness of some logical state manipulation with these axioms. And that's a fair point. But in some sense, this is like how verification works, right? You have some code, it does something physically on state, and the structure of many proofs about this kind of code is that you sort of develop a mathematical model and you sort of reduce the problem to proving some theorems about some mathematical model. Now the difference here is that it's not a pure mathematical model. This is actually talking about state just at a logical level in Iris rather than physical. But yes, indeed, there's still this question. How do you know these axioms I just threw up on the slide are sound? And that's a very good question. And the answer is we have a good story about this. So basically, the Iris approach to proving soundness. So in Iris, we call this kind of thing, like these axioms that I threw up here, we call this a ghost theory. And when you can state such a ghost theory, and then you can establish soundness of it using the following recipe. First of all, you have to define the model of these predicates like count and arc, okay? And you do that in terms of essentially some kind of partial commutative monoid or PCM. And this is not surprising that you would use a PCM. So in case you don't know PCM, it's just it's a set with a composition operation that's associative and commutative. The reason you use a PCM is very natural. That's the structure that's required by separation logic, essentially. The original separation logic is modeled using a PCM of heaps, in other words, partial memories with disjointness being the notion of composition. But you can define, the point in Iris is you can define whatever PCM you want, and you can use that to represent the logical state. And then Iris gives you 2 primitive proof rules for reasoning about this. One of them allows you to split up ownership. I'm just throwing this up here to give you a sense of what it looks like. One of them allows you to split up ownership. So if I have ownership of the composition, this is the composition operator. If I have ownership of the composition of two elements A and B, this is equivalent to owning A and separately owning B. Okay, so basically the resource composition operation is reflected in the separating conjunction. The other one is a little more interesting, and that is it says how you can change your logical state, how you can update it. So it says if I want to update ownership of A to ownership of B, and notice, by the way, you'll notice this funny three-lined arrow. Okay, this is subtly different from this two-lined arrow in a way that I'm not going to really explain. But basically, this is the two-lined arrow is just implication. Okay, ordinary implication. So in other words, implication, the thing that before the arrow and the thing after the arrow are talking about the same resource. With update, you actually are changing the resource under the hood. Okay, and the idea is you're allowed to change A to B so long as you can show that it is what is called a frame preserving update, meaning that for any frame F, which you can think of as all the other resources in the world that currently exist, okay, if I assume, as I'm allowed to do, that my own, the thing I locally own, A, composes properly with all the other things in the world, F, then I have to also show that once I change A to B, that B still composes well with F. Okay, so basically there's a global invariant which says that all the resources that all the threads own, together with all the resources that back up all the shared resource invariants, the composition of all those things is well defined. And so if you change any one thing, you have to make sure you don't break that global invariant of well-definedness of the composition of all the resources. And with these two rules, you can prove a lot more complicated ones. In particular, this kind of rules that I showed on this slide from all these previous logics, you can verify rules like these in Iris as well, and they're derived. They're not built into the logic, right? So you just derive them using these basic primitive rules for manipulating logical state and invariance. Okay, so wrapping up, I've talked about Rust. It's pretty cool, exciting language for becoming a sort of safe systems programming language, and its safety is quite subtle. And we've been developing this entire sort of formal foundations for Rust based on a semantic safety approach, where we interpret the safety of, or we interpret Rust types into Iris. And Iris has proven to be a really flexible logical foundation for doing this, and for a number of other projects. I encourage you to check out all our papers on Iris and RustBelt on our websites. If you're interested in more, there's a lot of interesting stuff going on. Or feel free to ask me questions about it. And I want to also thank all my collaborators. I've had many fantastic collaborators on this project. Thanks a lot. Sorry I went over by 15 minutes.
Oh, it's fine. You had a lot of questions, so great. I mean, I think since we've had, there's no outstanding questions, and we've had a bunch. So
if anyone has, hi Tadeusz.
Oh, hi, Derek. Actually, I do have a question, but it's a long one.
Sure.
I'm not sure if I ask. So it is about this additional line of work you mentioned, which is supposedly another fundament of RustBelt, the GPS thing. While we were talking, I was not aware of this actually. So while we were talking, I looked it up, and it seems that the last thing in this line is 2017 ECOP paper, right? Because
that's one of the versions. So the original version was OOPSLA 14, yeah, the one that was done we then showed how to actually encode GPS in Iris and actually improve on it in Iris, and that was done in 2017. Yeah, but then we used an extended version of iGPS. So iGPS is the Iris version of GPS, and we used an extended version of that to adapt the original RustBelt proof, which was done under a sequentially consistent memory model, to one that's based on the C11 memory model and uses relaxed operations.
Mm-hmm. Yeah, this sounds very interesting to me, because I have colleagues or friends who are interested in doing verification of C memory models or things related to it, like C minus or CMM, which are used in lower levels of compilations for even languages like Haskell, in fact. But it seemed to me, or it seemed to them, that most of the stuff that was happening in the C ecosystem was mostly the Apple stuff, so the deep spec. And even though when I was talking to people from Europe, like Pierre Évariste Dajant, he was telling me that if he was ever to update or save saved this famous Koch world's best macro assembler paper from further rusting, no pun intended. He would do it by moving to Iris, but on the other hand, when I was looking at the developed things that were happening, they were mostly in related to Rust. I was wondering if there is anything of interest, or well, not of interest, of course of interest, but suitably developed to be a real life development outside.
Well, I guess the question is,
Rust.
what do you mean by real life development? So I mean, yeah, I mean, there's most of the work that we've done so far in Iris has been focused on, core calculi that represent interesting languages, and then we, but they're mostly focused on core calculi, not running languages. So even the work we've done here is done in this language called Lambda Rust, which is a pretty fully featured core calculus that represent. It's intended to be relatively close in spirit to the mirror in Rust, the intermediate representation in Rust. But it's not the full source language. Okay. We do have some work which I'll actually be presenting in some talks next week on a version of on applying Iris to verifying C code.
Okay.
With automatic verification that produces Iris proofs, but that's very new work. So in the past, it's been mostly applied to, and that's very new work, and that applies to actual C code. But in the past, yeah, we've mostly been focused on sort of exploring programming language meta theory and building foundations for type systems and the kind of stuff I've talked about here. That said, like when we verify stuff in Lambda Rust, the Lambda Rust code looks like, I mean, it's not very far off from the Rust code. It's a lot of the applications of Iris so far have been to verifying really complicated things about really small pieces of code, where we saw in the ARC example, right? It's like one line of code for clone, but it's doing some pretty fancy ghost state manipulation and so forth in there. But yeah, we have a line of work on building separation logics for relaxed memory, and my student Hai Dong, who's mentioned here, his thesis work is all about that, and he's continuing to develop it.
Okay, very good. And where is this talk next week supposed to happen?
Oh, well, I'm giving one version at the OWL seminar.
Okay.
That's the more, I think that's the more publicly attendable one. I'm giving it at some other institutions, but yeah, next Wednesday.
Okay. Oh, that will clash with my teaching probably, but okay. Good to know.
I think it's recorded. I think they're all recorded.
Okay, good.
Cool.
Anybody
else have any questions? Or?
Yes, go ahead.
Right. Thank you for the talk. It was very interesting. I've never had the chance of looking deeply into Iris, but I was introduced to it by Amin Timani, who is one of your collaborators when he was still in Belgium, where I am at the moment based. So my first reaction to the rules in Iris that he showed me was that who gets to read these? It's just who gets to read these rules? They're just so big and involved and
which rules were you talking about?
Like the derivation rules of the logic.
Oh, you mean you're referring to like those rules?
That one.
Yeah. So
those three.
So the good news is we don't actually work with these rules. We, in some sense, originally our thought was that you would want to, was that we wanted to have all these fancy rules from different logics, and so that we wanted to have a uniform way of deriving them. But in the end, actually, we end up working with the basic rules most of the time, because basically we end up having certain constructions on these PCMs that we use all the time, and then we use those to derive sort of specific ghost theories, like this one, for example. Right. So this is a kind of data structure specific ghost theory, a bunch of axioms that are specific to the kinds of predicates you actually want to use in reasoning about this particular data structure. And we will verify those, that sort of that more specific kind of set of axioms, and then we work with those. And we do it for each kind of we do it period. And I would say, by the way, in many cases, you see very common patterns. And so you don't even have to actually go to the trouble of defining a whole ghost theory. You just work with standard PCM combinators. So for example, one of the workhorses of Iris is something called the auth monoid, which is represents the authoritative PCM. And it's this idea of there's some authoritative state, which usually gets put into some shared invariant. And then there's fragments of this state, which are owned by different pieces of the program. And then there's rules for saying if you have a fragment and you have the authoritative piece, how can you update the authoritative piece and the fragment simultaneously? And you'll see that in this example, this is just an instance of the auth monoid. Here, the count predicate is the auth predicate, and the arc predicate is the fragment predicate. And so this kind of ghost theory, although I just came up with it for this example, is an instance of this auth, is a direct instance of the auth pattern, and we use that all over the place. And so, as far as I know, no one had articulated that auth pattern before, but that seems to be much more handy in many cases than these.
Sure, but if I'm about to read the paper in which this is written,
yeah, don't read this one.
Then that means that the community will get isolated over the years. I mean, at least in some way, because no one can penetrate. I mean, many few people.
Yeah, but that's part of the point here, is that you don't actually have to read all these rules. You don't have to understand most of these complicated proof rules because we don't end up using them. We use a much simpler set of proof rules, and I mean, basically, we have tutorial material on Iris. You can read about common constructions that we use there. In practice, what people do is, so actually, one thing we would like very much to do that we haven't done so far is write a paper on going through all the common constructions that people really use in Iris proofs. We don't actually have such a paper right now. They are described in some of the papers that we've written, but we don't have one place to look for the standard constructions, which are much simpler than this.
Right.
But that's something we'd like to do. That said, mostly what people do is they start programming, they start using it in Conc, and then they see the rules that are used in common in existing examples, case studies, and then they use those.
Right. Okay. Harley, I don't know whether it's just me or not, but if you pay attention to my picture, you will notice that it's flashing from time to time. The presentation gets black every now and then it gets back to white. I'm not sure what the reason is.
I haven't seen that over here.
Okay.
It doesn't look like it's on the YouTube, doing it on the YouTube either.
Right.
Not sure.
Okay, possibly me. Fine.
Yeah, thanks.
Thank you.
I'll definitely keep an eye on
it
that.
just happened. It just happened now.
It did?
Yeah, nothing happened.
Yeah.
Okay.
Yeah, not sure.
Right. Okay. Thank you. Anyway.
Sure.
Okay, great.
I think there is very interesting question on YouTube. So about using Iris for things outside of safety.
Where's the?
Oh yeah, sorry, I missed this one. Yeah, it says, can you say more about using the Iris for things outside of safety? For example, Popple 20, there was a probabilistic model for BI. Could I add logical state for probability distributions and do crypto proofs, for example, where BI is bunched implications? Right.
Good question. So I don't know about probabilistic BI. We have not yet tried to do instantiation of Iris for reasoning about probability. Yeah, that's a very interesting direction. We haven't tried to do that. We just recently have done some work on a variant of Iris that is capable of supporting liveness properties. So this is brand new work because basically Iris, for various reasons that are hard to go into without getting more technical, Iris is what's called a step index program logic. So it's based on a model of a step index model. That doesn't mean anything to you. That's fine. If it does, then you will probably recognize that with a step index model, essentially the meaning of assertions in the logic is sort of stratified into intuitively, it's stratified into a family of assertions that are indexed by this natural number, and that sort of says like, that gives you the meaning of the assertion up to observing n steps of computation, if n is the number. Okay. That's not exactly correct, but that's roughly the idea. And so because of that, Iris is only capable in its current form of proving safety properties, because it can only talk about properties that hold under, that are described by the finite prefixes of a computation. But we have this work on something called transfinite Iris, which is adapts Iris to a transfinitely step index model where we model step indices as ordinals instead of natural numbers. And then we're actually able to prove Leibniz properties. But we've just done the first work on that. There's a lot of work left to be done to explore, to make the logic richer and more powerful.
That sounds cool, though.
Yeah, I'm excited about that.
All right. Unless I missed any questions, I think we got them all.
Cool. All right. Thanks
Cool.
a lot.
Yeah.
Arlie,
Thanks a lot. I really appreciate you giving the talk. It was really good. Thank you.
Not at all. Thank you.
See you, everyone.
Thank you. Bye.
Thanks.